So now I'd like to invite our next speaker, Thomas Thoms from EMC, Energy Materials Corporation, and I'm really happy that you are presenting. I've been trying to convince him to present for almost 3 years now, so really happy about that. And he'll be telling us about commercializing high-speed production of perovskite solar panels. So please. I think we're going to change the slides for you. Let's see.
Yeah, so I've been spending my whole career commercializing printing technologies and materials and equipment. 6 years ago, I joined Energy Materials Corporation, EMC, and to use this to develop a printing technology to print solar panels. And I'm going to go through, what it takes to do that, but first I'll start with why. Why do that? Demand for solar is generally described to be, off the charts, right? Most credible organizations peg that at around 75 terawatts of need by the year 2050. That's a lot of solar panels. Right now, there's about 1 terawatt installed, so there's a long way to go. So how do you get there? Today, the supply is about 360 gigawatts per year. So in 100 years, maybe you get halfway there. But solar panels don't last 100 years, they last 20 years or less. So you really need to ramp up the supply of making solar panels. So there's really a significant need that's well recognized. There are some challenges in using the existing technology. The existing dominant technology is using silicon wafers, right? It's a difficult manufacturing process. It requires a lot of energy. Because it requires a lot of energy, the energy needs to be super low cost, so that limits where you can do this. The CapEx for making the equipment for all these factories is quite high, and the labor costs are high. But China has managed to, through massive subsidies, to sort of create a global monopoly. So that's where we stand today, and our technology is to disrupt that global monopoly. So how do we do that? First off, is using a different technology called perovskites. So perovskites is really just a crystal structure. It was a mineral, naturally occurring mineral that was discovered in the 1800s. Much more recently, it was shown that it's an absorber. It can be made into a solar cell. And very quickly, once that was discovered, the performance of this perovskite absorber has been shown to be as good as silicon, better than any other thin film technology. The next best thin film technology that's commercial is cadmium telluride, and you could see that perovskite surpassed the performance of cadmium telluride about 10 years ago almost. And every other thin film technology. And it's about 5 years ago, it's about the same performance as the dominant silicon technology. A few years ago, it was shown in accelerated tests that could be as durable and have as long life as traditional solar. And so now we have a new technology. And so why choose this technology? And it's the same performance. Well, the one reason is that you can print it. You can print it at high speeds, and you can't do that with these other technologies. So why can you print it? It's because you can dissolve it in a solvent and print it, and turn it into an ink, print it, and then dry it, crystals form, and now you have a perovskite absorber that you can print. Of course, you need to print more than just the one layer. There's other layers that are needed. There's other functional layers. I show them up here on the right. They need to be printed. They need to be put on top of each other. But if you can do this all at high speed, all in line, then you're essentially go into a factory with a roll, and you come out with a roll of solar cells, right? And which is a much simpler process. So how does that work? So if you look here, you see a bare roll of essentially flexible substrate. Typically, it's a plastic like polyester, low-cost plastic. And you unwind it, and you put it into this printing machine. It goes and prints these layers, and then after each layer, it dries the layer. It turns it in. It gets rid of the solvents, so you have a thin film. This is a pretty traditional manufacturing method.